In lecture 4, we will mainly discuss the AND gate properties. We will discuss the symbol of AND gate and operation of AND gate and the truth table of AND gate, the timing diagram and the Boolean expression. And we'll also discuss some relationship between this OR gate and NAND gate and some examples of NAND gate operation and the practical IC which used to perform this NAND gate operation. Okay. And first, we will discuss why this NAND gate and OR gates are called universal gate. Okay, so this is a common term. NAND gate and OR gates are universal gates. Okay, why they are called as universal gate? Because they can perform all the logical operations of basic gates like AND, OR, NOT. Okay, by using NAND gate, we can implement AND function, or by using NAND, we can implement OR function. Similarly, the NOT function. So that's why this NAND gate is known as universal gate. Similarly, when you discuss the next lecture, we will discuss the NOR gate property. By using the NOR gate also, you can implement AND or NOT gate. So one more thing, usually we'll call this AND or NOT are the basic gates, and NAND and NOR gate are known as the universal gate. So don't get confused with basic gates and universal gates. And usually we'll use basic gates for AND or NOT. Okay. And after 2-3 lectures, we will discuss how we can implement AND by using NAND, and similarly OR NOT by using NAND and NOT. Okay. In this lecture, we will discuss the other properties of NAND gate. And so first point we already discussed is also known as a universal gate, and NAND gate means actually AND function and the complement. Okay, so there will be an AND gate. Okay, and the output of AND gate is complemented. So that gate is known as a NAND, and this is the symbol used to represent a NAND gate. So this bubble is actually indicating the NOT operation. So AND then NOT operation. And so the working of NAND gate we can define. It produces a low output only when all its inputs are high. Okay, or we can say that the output will be high. Output will be high when any of the input is low. Okay, in this way also you can define this AND gate operation. And now we'll see the truth table of NAND gate. We already mentioned that if any one of the input is low, output is high. So here you can see the input is low, so output is high. Here one input is low, so output is high. Here one input is low, output is high. And here both the inputs are high, so output is low. So this is a truth table by using this binary bits. 0 0 is 1. So here 1 0. Here, okay, if any one of the input is 0, the output is 1. If all the inputs are high, the output is 0. Okay. And similarly, we can write this for n number of inputs. And for example, this is n is equal to 2. So you will get 2 square, 4 different combinations. Okay. If n is equal to 3, means AND gate with 3 inputs. For example, A, B, C, 3 inputs. Then you need to write 2 raised to 3, you will get 8 combinations. So you need to write 8 combinations like this: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay, you'll get 8 combinations, and let it be A, B, C, and the output. Okay, you can write any one of the input is 0, output is 1. So all these cases you will get output is 1. When for the last case you will get 0. So this is a 3 input NAND gate operation. And similarly, for any number of input, you can write the truth table. And now we'll discuss the timing diagram concept. And timing diagram means it's actually graphical representation of this binary. So here you can see that 0 0. Okay, if it is 0 0, output will be high. Okay, you need to expect a high here. So here it is 1 1. So you need to expect 0. So 0 1. So you need to expect 1 1 1. It will be 0. And 0 0, output will be 1, again 1 0, output will be 1. When it is 0 0, output will be 1 1 1, output will be 0 0 1, output will be 1 1 1, output will be 0 0 0, output is 1. Okay, you can also draw the waveform. Okay, this is a graphical representation, or you can call it as a timing diagram. Now we'll discuss the Boolean algebra. Boolean algebra means we are representing the NAND gate operation by using variables and operators. Okay, so here you can see that if this is the NAND gate, and let A and B is represented as the input and X output. So this X output we can write here, it is A into B, the AND operation, then we need to perform a NOR. Okay, so this is the NAND operation. So don't consider as this is not equal to A bar B bar, okay, which is wrong. Okay, this is the correct representation, A B the whole bar. So never write NAND operation like this, A bar into B bar. Okay, we need to put the whole bar. So here you can see the expression also, 0 0. You can see first we need to perform the AND operation, 0 and 0, so we'll get 0, and then perform the NOT operation. Similarly, if you take 1 0, first we need to perform the AND operation, so answer is 0, then you need to perform the complement, you'll get 1. And the last 1 1, we perform 1 1 AND operation, is 1, then perform the NOT, so you'll get 0. So this is a Boolean expression. And now we'll discuss one property of NAND gate. This is commonly used in circuits. Negative OR is equivalent to NAND operation. Okay, so this is NAND, and you will get the same result when you perform the negative or bubbled input. Okay, or we can call it as a bubbled OR. Okay, so we can call this circuit as bubbled OR. Whenever there is a bubble, means that's a NOT. For example, if the input is AB, at the output side you will get A B bar. So when you perform this gate, here you can say you are connecting A, and here it is B. And before applying the input, we will make it the complement. So you will get A bar, okay, then B bar. So here you will get B bar when you perform the bubble. So not operation. Then you need to perform the addition. So this is equivalent to A B the whole bar. Okay, we can prove this. Simply you can write A B, and you can perform A bar B bar. Then you need to perform A bar or B bar. Okay, if you write this table, and if you verify the result, and okay, so 0 0 0 1 1 0 1 1, and if you take the complement of A, it is 1 1 0 0. You take the complement of B, 1 0 1 0. Okay, now we need to perform the OR operation between these. So 1 or 1. Okay, 1 or 1 is equal to 1, and 1 or 0, it's 1 0 or 1, it's 1. Okay, 0 or 0 is equal to 0, so which is equivalent to A B the whole bar. Okay, which is the AND gate truth table. So if you verify with the previous one, sorry, not AND, this is an AND. Okay, okay, this is an AND gate. So an AND gate output, when it is 0 0, we'll get 1, and here it is 1, here it is 1, and here it is 0. So if you verify these two table, they are equal. Okay, so we can call it as bubbled OR is equal to NAND. Okay, instead of drawing the NAND gate, sometimes they will give in the circuit this bubbled OR, so which is equivalent to NAND. Okay, and another concept, the enable and disable input of NAND gate. For example, if any one of the input of the NAND gate, it's 0, means, for example, this A input is 0, and B input is can be anything. Okay, so irrespective of the input B, when A is 0, the output will be 1 always. So there is no important if it is B is 0, B is 1. The output will be always 1, because any one of the input of NAND gate is 0, the output is 1. So we can call it as the disabled input of NAND gate, that's 0, and the enabled input is 1. Okay. And we'll discuss now one of the application of NAND gate. So we can consider chemical manufacturing industry. Okay. Here we can see that there is a tank, and the tank contains a sensor, and it detects when the chemical drops to 25% of the food. When the sensor produce a high level of 5 volt when the tanks are more than 1/4 foot. So when the tank contain more than 25 percentage, okay, we will get a high load. Okay, when it is less than 25 percentage, it produces a low. That's a condition, and it required that a single green LED light, LED will indicate, shows when both tanks are more than 1/4 foot. Okay, we need such a logic. So here you can see here also the same function. If it is less than greater than 25 percentage, it will produce a high output. Less than 25 percentage, it's a low. So assume that both tank contain more than 25%. So here you will get high. Here also will get high. If both inputs are high, the output will be low. And this LED is connected in the syncing board. So here is the plus 5 volt. So here it is plus, and when the output of the NAND gate is low, here you can see the LED will be in forward bias condition and the LED will be in the. Okay. In all other cases, when this tank content is less than 25 percentage or 0, it becomes low. If any one of the input is low, the output is high. Okay, or plus 5 volt. So in that particular case, you can see that one end it is plus 5, another end is also plus 5. So there is no potential difference. LED will be in the off condition. Okay. And this is the practical IC we used in to perform the NAND gate, and we can call it as 7400, 7410, 7420, 7430. But very important, it's 7400. You can see that the series starts from 00. The first number is given for the NAND gate. Okay, and here you can see there's a 2 input. Okay, 2 input NAND gate, and it contain 4 gates. And here you can see that this is a 3 input NAND gate, and it contains 3 gates. Here you can see that 1, 2, 3, 4. So 4 input, and it contains 2 gates. So here you can see that 1, 2, 3, 4, 5, 6, 7, 8. So 8 input and 1 gate. Okay. So NAND gate is very popular. So that's why we are discussing more number of ICs. Okay. But 740 is very common, and definitely you need to remember the pin out of the 7400. Okay. You can apply input at 1, 2, and you can take output 3. Another 3 and 4 you can apply input. 6 you can take output. Here 10 and 9 will act as the input. 8 output. Here 11 output. 12 and 13 input. VCC 14, 7 ground. The same similar operation you can expect in other IC also. Okay.